Hi everyone, my name is Sarat, and in this video, I'll be presenting our work on efficient graph construction for image representation. To give a high-level overview, we summarize here our contributions. Graphs are useful representations capable of capturing complex relations in data. Recently, graphs constructed on images have been used for spectral image analysis and several image filtering operations. However, the graph construction itself, which is generally made up of several million nodes and edges, is often overlooked. Our key contribution in this work is a scalable graph framework based on our recent work, non-negative kernel regression. We perform specific analysis to extend this graph framework to the domain of images. The resulting image graphs have far fewer edges than standard approaches. For example, our proposed graph construction framework produces a 90% reduction in edges compared to a standard 11 by 11 window-based graph. This consequently speeds up graph filtering operations by a factor of at least 15. We show experimentally that NNK image graphs are indeed better representations. We observe improved energy compaction and better denoising performance using spectral graph wavelets and our graph framework. Now, to formally motivate the problem, we first answer the question of why we need graphs for images. Image processing over the past years has evolved from simple linear averaging filters to highly nonlinear image-dependent filtering operations. For example, the bilateral filter. The problem, conventional analysis based on Fourier and other grid-based transforms, no longer apply. A popular recent alternative is that of graph-based spectral analysis. In graph signal processing, one represents images as graphs and observes the intensity or segmentation labels on the images as signal. The eigenspectrum of graphs provides a frequency basis structure similar to that of Fourier, referred to as the graph Fourier transform or the GFT. Now then, what is the right graph representation for an image? An image graph is often constructed with each pixel as a node, with edges between them capturing similarity between the nodes. A standard naive approach for representing images using graphs is that of a window-based method. Each pixel node is connected to all neighboring pixels within a window centered at the pixel. These are then weighed using a kernel, such as the bilateral filter kernel from previous slide. Note that this approach is equivalent to a k nearest neighbor approach, where we select k according to the number of neighbors in a given window size. A problem with this kind of graph construction is that the sparsity of the image graph is based on an ad hoc parameter, namely the window size. As an alternative, we consider here a recent work on graph learning, the non-negative kernel regression graph. NNK graphs considers the problem of graph construction from a sparse signal approximation perspective and is optimal from this point of view. Further, they have interpretable connectivity where edges are defined by the local geometry of data and is robust to hyperparameters. To briefly introduce non-negative kernel regression graph, we outline here the basic idea behind the graph framework. Consider this setup. For each node I, select nodes j with maximum kernel similarity value. These selected nodes can be considered to form a locally adaptive dictionary. Now, observing similarities as inner products in a kernel Hilbert space, we see that a k nearest neighbor approach follows a thresholding-like process wherein selecting k maximally correlated atoms in the dictionary formed. This is suboptimal from a signal processing perspective. As an alternative, NNK graph poses the problem in the form of non-negative basis pursuits to obtain an efficient representation. The optimization involved in NNK graph can be written in terms of only similarity information. To exemplify the characteristic of NNK graph, we consider here a toy setup involving 7 data points. Unlike the KNN graph on the left, where the connectivity is entirely dependent on the hyperparameter k, the relative position of each neighbor is taken into consideration to obtain a stable sparse representation in NNK graph. The sparsity in NNK graph is thus dependent on the local geometry of data and is not dependent on a single ad hoc hyperparameter. This property of NNK can be theoretically and geometrically explained using the kernel ratio interval, which states the necessary and sufficient condition for two nodes to be connected. Simply put, given a node J connected to node I, NNK looks for additional neighbors that are from a different direction, in other words, orthogonal. For example, in the figure on the left, node K and everything beyond the plane formed by node J will not be connected to node I. Applying this hyperplane argument inductively gives us a convex polytope around each node. Naive application of NNK graphs is cubic in the size of the windows, which soon adds up and becomes infeasible for large images. Further, NNK graphs does not exploit image-specific properties such as pixel position regularity. So then the question is, can we do better in images? Consider the bilateral filter kernel as an equation. Here, xi and xj denote the position of the pixel, that is, row and column in the image, and fi and fj corresponds to the pixel intensities at these locations. Applying the KRI condition with bilateral filter kernel gives us a simple condition to determine if a pixel k is to be connected given a pixel j is connected to node I. Due to the regularity of pixel position in images, the term on the right of the equation is independent of the image and can be pre-computed. We will use this condition with positive thresholds, the reason for which will be explained as part of the algorithm to prune pixels in the window, thereby reducing the complexity associated with applying NNK for constructing graphs and images. To better understand the proposed method, let's walk through a simple example to clearly understand each step involved in the proposed NNK image graph. Consider a 7x7 window centered at pixel I. Previously, one would connect all the pixels in this window to node I to form a graph. Now, for NNK, start with one of the closest pixel, namely J, and assume it's connected. Given this setup, the pre-computed threshold condition associated with each neighbor is as shown in the figure. It is highly unlikely that node J will affect the connectivity of pixels in the negative delta region. And hence, without loss of generality, we can focus on pixels with non-negative threshold. Now, pixels with intensity similarity below the threshold are zero-weighted, that is, will be disconnected and can be pruned. We perform this step iteratively, selecting closest pixel that is not pruned, following which we apply condition to remove pixels that are below threshold till we have no more pixels for processing. This greedy setup allows us to achieve speedups in the order of 10x compared to the naive approach of applying NNK. Further, we approximate the edge weights corresponding to selected nodes using the original kernel weights, as NNK maintains the relative importance of the neighbors. In the following slide, we show experimental performance of proposed NNK representation using spectral graph wavelets. The spectral graph wavelet decomposition of a commonly used image with bilateral filter graph in the top row and proposed NNK graph is shown in figure. Frequency of the wavelets increases from left to right. The amount of information in a particular frequency band is proportional to the variance of the image in that band. As can be observed, wavelets corresponding to the proposed NNK method captures most of the image in its lower frequencies, indicative of a better image representation. Next, we consider the problem of image denoising to evaluate filtering performance. We compare the performance of our method in conjunction with spectral graph wavelet to that of the bilateral filter graph and the original bilateral filtering method. We also compare our method to the BM3D method. The average performance over 12 images at 5 different Gaussian noise levels is shown in the plot. As can be seen, in terms of both PSNR and SSIM, the proposed NNK graph based on simple bilateral filter kernel improves performance significantly. To conclude, we presented here a scalable, efficient graph framework for images with interpretable connectivity and robust performance. By performing image-specific analysis, we were able to achieve 10 times faster runtime compared to naive NNK graph construction. Further, the local nature of the algorithm allows for parallelized execution and will be evaluated in the future. We would be glad to answer your questions and comments via email. The MATLAB code for the method can be found at our Stack USC GitHub repository. Thank you.